In previous chapters, we have noted one of the most important characteristics of a dynamical system as stability. A formal definition of stability can be made in several different ways. Nevertheless, loosely speaking, you can call a system stable if it can restore equilibrium conditions after a perturbation. You can call it critically stable if the response exhibits sustained oscillations or it varies in a bounded way. And the system will be unstable if the transient response increases unboundedly. In order to study stability for linear time invariant systems in general, let us first generalize our findings about second-order systems to higher-order systems. Here is a basic feedback configuration. Note that both the feed-forward transfer function g of s and the feedback transfer function h of s are real rational functions. In other words, they are ratios of two polynomials in S. Using simple block diagram algebra, we can write the closed-loop transfer function in terms of these polynomials p, q, n, and d, and the result will be again a real rational function. If both transfer functions g and h are strictly proper, the degree of the denominator polynomial of the closed-loop transfer function will be determined by the q and d polynomials, and the closed-loop transfer function will also be strictly proper. Let us now consider factorized forms of the numerator and the denominator polynomials in first-order factors. Here, z and p parameters can be real or complex. Nevertheless, if they are complex, we know that they will exist in conjugate pairs. Now, if the input is a unit step function, we can write the Laplace transform of the output as a partial fraction expansion, and the a parameters in this expansion can be obtained by the residue theorem. In fact, this expression tells us that besides the forced part of the response, which is represented by the first term of C of S, that is A0 over S, the response of a linear time invariant system with all poles on the left half plane is a sum of decaying exponentials or damped oscillations. In other words, if all poles of the system have negative real parts, the natural response will approach to zero. For example, if the closed-loop transfer function has one real pole and a pair of complex conjugate poles with a real zero, the unit step response can be written as the sum of three terms. The first term, which is a step function, represents the forced response. The second term will be a decaying exponential if the pole minus p1 is negative. And if the real part of the complex conjugate poles is negative, zeta omega n will be positive, which means the last term will be a damped oscillation, which is going to die out to zero. Note that the zeros of the transfer function do not play any role in whether we'll have rising or decaying exponentials or oscillations in the response. They also don't affect the decay rates of exponentials or frequencies of oscillations. They only contribute to the amplitudes of them. At this point, we can also distinguish between negligible and dominant poles. For example, if a real pole is far from the origin in the left half plane, the part of the response corresponding to this pole will be a rapidly decaying exponential and will have a relatively smaller residue. Therefore, its contribution to the response may be neglected. On the other hand, if a pole on the left half plane is very close to a zero, it will also generate a small residue. So to speak, you will have a pole-zero cancellation. You can also neglect such poles. That means the response will be dominated by the poles which are closer to the imaginary axis and which do not have any zeros nearby them. We can conclude from the discussion up to now that the absolute stability of a closed-loop system can be maintained by avoiding poles on the right half complex plane and on the imaginary axis. In fact, poles on the right half plane will result in increasing exponential or oscillatory response. Poles on the imaginary axis will cause sustained oscillations. And poles on the left half plane will result in decreasing exponential or damped oscillatory response. Further, for a more satisfactory response, the poles of a system are usually required to be not only in the left half plane, but to be confined in a smaller region in there. For example, it is this region where we would like to have our poles in if the damping ratio is required to be greater than 0.4, or the magnitude of the real part of the poles has to be larger than sigma if the settling time is required to be less than 4 over sigma. You can find out by yourself how the regions where one should place the poles look like for other types of time domain specifications. So, the stability of a linear time-invariant system described by a real rational transfer function given as a polynomial b over polynomial a depends on the locations of the roots of the denominator polynomial a. In other words, to determine whether the system is stable or not, we have to find out whether the equation a of s is equal to 0 has roots on the right half complex plane or not. This equation we are going to call the characteristic equation of the system. Even for polynomials of modest order, finding the roots themselves may be quite difficult. So the question at this point is if we can determine whether the system is stable or not without finding the roots of the characteristic equation. Routh's stability test provides a simple solution for this question. The test is conducted in 3 steps, and the first 2 steps can be applied by direct inspection of the polynomial a. If the constant term in a polynomial is 0, that means we have poles at the origin. So we start by removing 0 roots from the characteristic polynomial. For the rest of the test, we can assume that the constant term of the polynomial, that is a sub n, is non-zero. In the second part of the test, we check if the sign of any one of the coefficients is different than those of others, or if a coefficient is 0. Because if so, that would mean there is a root or are roots of the polynomial on the imaginary axis or on the right half plane. For example, if the denominator polynomial of a transfer function is s cubed plus 3s squared minus 4s plus 2, then we can directly tell that the system is unstable simply because one of the coefficients is negative while the others are positive. Also, s to the 5 plus s to the 4 plus s squared plus 4s plus 2 is an example for a denominator polynomial of an unstable system because the third power of s is missing in this polynomial. To find out why, let's consider a factorization of the polynomial a where the first order factors correspond to real roots and the second order factors correspond to complex conjugate roots. If the real roots are negative, that means P1 to Pk are positive. On the other hand, C coefficients are some of the squares of the real and imaginary parts of each root, so they must be positive as well. Finally, the B objects are given as minus 2 times the real part of each root. So if the real part of complex roots are on the left half plane, B1 to Bj are also positive. Therefore, the sign of the coefficients A1 to An is determined by the sign of a sub 0 and the signs of all coefficients are the same if the roots are on the left half complex plane. Still, a polynomial can have poles on the right half plane even if it passes the first two parts of the test. So we proceed to the third step. In the third step, we are going to build an array using the coefficients of the polynomial, the so-called Routh array. To write the first row, we start from the coefficient of the largest power of the polynomial and skip every other coefficient. That is, the first row is a0, a2, a4, a6, and so on. The other coefficients go to the second row in the same order. So in the second row we have a1, a3, a5, a7, etc. Note that the first row is called as s to the n and the second row as s to the n minus 1. That is the powers of s corresponding to the leading coefficients of each row. We are going to call the other rows in the same order. In a Routh array, the elements of each row are computed from the previous two rows as the negative of some determinants divided by the leading element of the previous row. The first column of these determinants are the leading elements of the previous two rows, and other elements of the previous rows are used for the second column. So in the third row, we have b1 as a1 times a2 minus a0 times a3 divided by a1. b2 as a1 times a4 minus a0 times a5 divided by a1. b3 as a1 times a6 minus a0 times a7 divided by a1. The next row is obtained using the same pattern. That is, C1 is B1 A3 minus A1 B2 divided by B1. C2 is B1 A5 minus A1 B3 divided by B1. And C3 is B1 A7 minus A1 B4 divided by B1. Other elements in this row is obtained similarly. Then follows the next row, that is the row for s to the power n minus 4 with d1 equals c1 b2 minus b1 c2 divided by c1, d2 equals c1 b3 minus b1 c3 divided by c1, and so on and so forth. As you proceed downwards in a Routh array, the number of elements in each row will decrease, so the array will terminate at the line called s to the 0. Now, by inspecting the leftmost column of this array, we can decide about the number of roots on the right half plane. Namely, the number of roots with positive real parts is equal to the number of sign changes in the first column of the array. In other words, you can say that all roots of a polynomial are on the left half complex plane if and only if all coefficients are positive and the first column of its Routh array is positive. Here we have some examples. The first polynomial we are going to test for stability using Routh array is s to the 4 plus 2s cubed plus 3s squared plus 4s plus 5. This polynomial passes the first two steps of Routh test. Namely, the constant term is non-zero, that is 5, and all coefficients of the polynomial are positive. So we proceed to the third step of the test. The first row of the array, that is s to the power 4 row, is composed of 1, 3, and 5. The other coefficients of the polynomial, namely 2 and 4, will be in the second row. In the third row, there will be two elements. The first one is 2 times 3 minus 1 times 4 divided by 2, that is 1. The second element is 2 times 5 minus 1 times 0 divided by 2, that is 5. The next row will have a single element, which is 1 times 4 minus 2 times 5 divided by 1, that is minus 6. There will be only one element in the last row too, that is a 5. Now, as we proceed downwards on the leftmost column of this array, we have two sign changes. One of them from positive to negative, and the next one from negative to positive. That means 2 roots out of 4 of this polynomial are in the right half plane. In the next example, let us find conditions on the coefficients of a third-order polynomial for stability. The first row of the Routh array will be A0 and A2. The second row is composed of A1 and A3. There will be only one element in the third row, which is A1 times A2 minus A0 times A3 divided by A1. Proceeding similarly, the last row will have only A3. Therefore, assuming all coefficients are positive, the condition for stability turns out to be A1 times A2 greater than A0 times A3. You can also say that for the stability of a third-order polynomial with positive coefficients, the product of inner coefficients must be larger than the product of the outer coefficients. Now, what if we get a 0 in the leftmost column of a Routh array? Let us examine this on an example. The polynomial we are going to test is s cubed plus 2s squared plus s plus 2. Note that the constant term is non-zero and all coefficients are positive. The first row of Routh array is 1 and 1, whereas the second row is 2 and 2. This configuration will generate a 0 as the leftmost element of the next row. Since we cannot divide by 0 in computing the elements for the forthcoming rows, we are going to use epsilon instead of 0, and after finishing the array, we are going to examine the signs in the leftmost column as epsilon goes to 0. So the element in the last column of the array will be 2. Now we observe in the leftmost column, if epsilon is negative, we have two sign changes, and for positive epsilon, there will be no sign changes. Since the roots of a polynomial vary with respect to its coefficients in a continuous way, we conclude that the roots must be on the imaginary axis for epsilon equals 0. That means the polynomial has no roots in the right half plane. However, it has a pair of purely imaginary roots. As the next example, let us consider the polynomial s cubed minus 3s plus 2. There is a sign mismatch among the coefficients in this polynomial, and also the square term is missing. So this polynomial has some roots in the right half plane. Still, the Routh array can tell us about the number of roots in the right half plane. The first row of the Routh array is 1 and minus 3. The second row would be 0 and 2. Nevertheless, we have to use an epsilon to proceed with the array. So the element in the third row turns out to be minus 3 minus 2 divided by epsilon. And the last row is just 2. For positive epsilon, there are two sign changes in the leftmost column, namely from the second row to the third, and from the third row to the fourth. On the other hand, for negative epsilon, we again get two sign changes, this time from the first row to the second, and from the second row to the third. That is, regardless of the sign of epsilon, for small epsilon, we have two sign changes in the leftmost column of Routh array. Therefore, this polynomial has two roots in the right half plane. Next, continue with a more pathological case. Namely, let's see what happens if we have zeros in an entire row. Here's an example. The polynomial a of s is s to the 5 plus 2s to the 4 plus 24s cubed plus 48s squared minus 25s minus 50. Since there is a sign mismatch among the coefficients, we know that there must be poles on the right half plane. But again, the Routh array can tell us how many poles are there in the right half plane. The first row of the array is 1, 24, minus 25, and the second row is 2, 48, and minus 50. So both elements in the next row will be 0. Such a case will occur whenever the polynomial has some roots in quadrantal symmetry. In other words, whenever there are roots which are symmetric not only with respect to the real axis, but also with respect to the imaginary axis. To resolve this case, we can write a polynomial using the coefficients in the previous row, starting from the power of that row and skipping every other power. This polynomial is called the auxiliary polynomial. In this case, the auxiliary polynomial will be 2 times s to the 4 plus 48s squared minus 50. Now, we are going to use the coefficients of the derivative of this polynomial to generate the next row. Now, having written the s cubed row as 8 and 96, we can proceed with the next row. That will be 24 minus 50. The element in the next row is 112.7, and the last row will be minus 50. Since there is only one sign change in the leftmost column, we conclude that there is one root in the right half plane. In fact, the roots of the auxiliary polynomial p of s are also the roots of a of s. In this example, since the auxiliary polynomial is in a double quadratic form, it is not difficult to find its roots. Defining x is equal to s squared, we can write the auxiliary polynomial as 2x squared plus 48x minus 50. And the roots of this polynomial turns out to be at x equals 1 and minus 25. Therefore, the roots of the auxiliary polynomial are at plus and minus 1, plus and minus j5. Having found 4 roots of a of s, the last one can be determined by polynomial division. And this root turns out to be minus 2. So we have 5 roots of a of s, 4 of which are in quadrantal symmetry, 1 root in the right half plane, and 2 roots on the imaginary axis. Routh test can also be applied for relative stability analysis. That is, to determine if the roots of a polynomial have real parts greater than, say, minus sigma, we can redefine our frequency variable s and apply the test on the resulting polynomial. The Routh test determines the number of poles on the right half plane. In other words, number of poles with real parts greater than 0. Now, if the poles of our polynomial are required to be not only on the left half plane, but also have real parts less than minus sigma, we can make a change of variable as s equals s hat minus sigma. So the condition real part of s is greater than minus sigma is transformed to the condition real part of s hat is positive. And the Routh test on the transformed polynomial can be used to check this condition. Let us consider the polynomial s cubed plus 8s squared plus 19s plus 12. We would like to determine whether this polynomial has roots with real parts between 0 and minus 2. We form the Routh array. The first row is 1, 19. The second row is 8, 12. The element in the third row turns out to be 17.5. And the element in the last row is 12. So we conclude that this polynomial has no roots in the right half plane. Next, let us make a change of variable and set s equals s hat minus 2. So the transformed polynomial will be s hat cubed plus 2s hat squared minus s hat minus 2. Applying the Routh test to this polynomial, we have 1 minus 1 in the first row, 2 minus 2 in the second row. That will generate a 0 in the third row. Therefore, we proceed with an epsilon, and the last row will be minus 2. Regardless of the sign of epsilon, we get one sign change in the leftmost column. Therefore, the polynomial in s hat has one root with positive real part. That means the polynomial in S has one root with real part being greater than minus 2. So we conclude that our polynomial has no roots in the right half plane. Nevertheless, it has one root with the real part being between 0 and minus 2. Finally, we will apply Routh's stability test in analyzing a feedback control system. Let us consider a system as in this block diagram. Our aim is to find the range of values for k so that the closed-loop system is stable. We can write the closed-loop transfer function as the feed-forward transfer function divided by 1 plus the open-loop transfer function, simplify it to a single fraction, and multiply out all factors. This gives us the characteristic equation as s to the 4 plus 3s cubed plus 3s squared plus 2s plus k equals 0. To determine how the value of k is related to stability, we form the Routh array. The first row is 1, 3, k. The second row is 3 and 2. The first element of the next row is 3 times 3 minus 1 times 2 divided by 3, that is 7 divided by 3. And the second element is 3 times k minus 1 times 0 divided by 3, which is k. The single element in the next row will turn out to be 2 minus 9k divided by 7, and the last row will be k. Since the first three elements in the leftmost column are positive, the last two elements are required also to be positive for stability. That means k should be greater than 0, and 2 minus 9k over 7 should be greater than 0. In other words, k has to be positive and less than 14 divided by 9. So the range of values of k to assure stability of this system is between 0 and 14 divided by 9. This brings us to the end of our discussion of Routh test and stability. Now, reviewing the exercises and questions in your textbook, check that you know how the stability of a linear time invariant system is related to the location of its poles, that you have an understanding of how the output behavior of a linear time invariant system is related to the location of its poles, that you can decide about the stability or relative stability of an LTI system using Routh tests, and that you can apply Routh tests in analyzing the stability of a feedback control system with respect to a parameter.